In this lecture, we're going to talk about another algorithmic technique called dynamic programming. And we're going to introduce dynamic programming by revisiting a problem that we've already seen, and that's computing the Fibonacci numbers. Okay, so remember that the Fibonacci sequence is the sequence of numbers 0, 1, 1, 2, 3, 5, etc. So in general, each number is formed by taking the sum of the previous two numbers. And we have the base case that the first number in the sequence is 0 and the second number in the sequence is 1. So we have this nice mathematical way to define what the Fibonacci numbers are, which I've written here. So the nth Fibonacci number is just n, if n is 0 or 1. And otherwise, if n is bigger than 1, then the nth Fibonacci number is the sum of fn minus 1 and fn minus 2. So we talked about this when we first started talking about recursive algorithms, and we saw that this mathematical definition was very easy to translate into a recursive algorithm. We can pretty much exactly write it in code, right? So we just have first our base case, so we check if n is 0 or 1, then we just return n as it says in the formula, and otherwise we return the sum of the evaluation of the function on n minus 1 plus the evaluation of the function on n minus 2. Okay, so we saw that this was very easy to code, but it wasn't actually a very good algorithm, right? So when we benchmark this algorithm compared to an iterative approach to computing Fibonacci numbers, where we, just compute the Fibonacci numbers in order, f0, we know that's 0, f1 is 1, f2 we can now compute since we know f0 and f1, then we can compute f3, etc. So we build up from the bottom up. So that's the iterative function that I'm comparing against here. And computing the 45th Fibonacci number, we see the recursive version takes almost 3.5 seconds, whereas the iterative version is under a microsecond. Okay, so the recursive version is more than 10 million times slower computing the 45th Fibonacci number. And we also talked about why this is the case, right? So when we look at the tree of computation for this recursive algorithm, the tree looks something like this, right? On Fibonacci of 5, we're going to call Fibonacci of 4 and Fibonacci of 3. Fibonacci of 4 is going to call Fibonacci of 3 and Fibonacci of 2, etc. And what's really bad here is that we're repeating work that we've already done, right? So you see that Fibonacci of 3 appears twice in this tree. And look at all the leaves of this tree, which are base cases, either computing Fibonacci of 1 or Fibonacci of 0. So you see that Fibonacci of 1 is repeated many times, right? 1, 2, 3, 4, 5 times. And Fibonacci of 0 is repeated 1, 2, 3 times, right? So we're computing the same things over and over again, which is quite wasteful, right? This is what's making this a bad algorithm. And we can even say a bit more concretely how bad this algorithm is. So let's just count how many leaves there are in this tree. So if we look at this tree, let's count how many leaves there are in general. And again, the leaves are just going to be our base cases, right? Computing Fibonacci of 1 or Fibonacci of 0. And there's a nice formula for the number of leaves in this tree, which is very similar to the formula for the Fibonacci numbers themselves, right? So in the base case, if we just compute Fibonacci of 0 or Fibonacci of 1, we are immediately in the base case, right? So there's only one leaf in this case. So in that case, the number of leaves is 1. And otherwise, the number of leaves in the tree for Fibonacci of n is the sum of the number of leaves in the tree for Fibonacci of n minus 1 plus the number of leaves in the tree for Fibonacci of n minus 2, right? So you see that here, every leaf in this tree here for Fibonacci of 5, we're basically just taking the tree for Fibonacci of 4, that's the left subtree of Fibonacci of 5, and we're taking the tree of Fibonacci 3, that's the right subtree. We put those together, that forms the tree for Fibonacci of 5. So the total number of leaves in this tree is just the number of leaves, in the left subtree plus the number of leaves in the right subtree. That's the number of leaves in Fibonacci of 4 plus the number of leaves in Fibonacci of 3. Okay, so we have this formula for the number of leaves, and you see it's actually very similar to the formula for the Fibonacci numbers themselves, right? They actually only differ in the base case. So basically this formula for the number of leaves, it just shifted over by one Fibonacci number, right? Because the Fibonacci of 1 is 1 and Fibonacci of 2 is 1. So it's like C of 0 is F1 and C of 1 is F2. And apart from that, they grow in the same way. So we actually have that the number of leaves in the computation of the nth Fibonacci number in this naive recursive algorithm is equal to the n plus first Fibonacci number. And the Fibonacci numbers grow very fast. The nth Fibonacci number is approximately 1.61 to the n divided by square root of 5. So the number of leaves in our tree grows very fast as well. And that's why this naive recursive algorithm is very slow, right? It's not a very good algorithm. Okay, so let's think about how we can improve this naive recursive algorithm. And we said that the reason why the naive recursive algorithm is bad is because we are repeating work, right? We're doing the same thing over and over again. So an easy solution to fix that is when we compute a value, we just remember it. And then if we want to compute that value again, we just look it up in some table, then we know the value, and we don't have to do the additional work to compute it again from scratch. Okay, so this is a technique called memoization. It sounds like memorization, but it actually comes from memo, like writing a little note to yourself, a memo. So now we're going to write this algorithm using memoization. And since now we're going to have a data structure plus a function, I'll just throw this into a little class here called Fibonacci. And we have a vector there called memo. And whenever we compute a Fibonacci number, we're just going to write it there in the memo. And the next time we need it, we can just look it up in this vector rather than having to recompute it again. Okay, so now here's what the functions look like. So the function here on the bottom called compute, it just does a little bit of setup. So we resize our memo to have size n plus 1 if we want to compute the nth Fibonacci number. So that can just hold the Fibonacci numbers 0 through n. And we initialize memo with the base cases, so we know that the 0th Fibonacci number is 0, the first Fibonacci number is 1. And then we call our recursive algorithm, which is at the top of the screen here, called Fibonacci helper. And our base case now becomes checking if the value is in our memo table already, checking if we've already computed the value. Okay, and we're just representing that by, if the value at a position of memo is non-negative, then that is the correct Fibonacci number there. And if it's negative, that means we haven't computed that value yet, because we initialized memo to be all -1. So our base case, we just check if we've already computed the value. If we have, we just use that. Otherwise, then we compute the value using in the normal recursive way. Okay, so this is an improved recursive algorithm using memoization. And we see that the running time is much, much better, right? So now I've looked at the running time computing the 70th Fibonacci number. And the recursive version is now under a microsecond. Okay, it's still a little bit slower than the iterative version, but much, much faster than our naive recursive version. Okay, so this is kind of our first example of dynamic programming. So dynamic programming is similar to divide and conquer in that we express the solution to the original problem in terms of similar subproblems, right? We're expressing the solution to computing the nth Fibonacci number in terms of computing the n minus first and n minus second Fibonacci numbers. But unlike divide and conquer, the hallmark of dynamic programming is that you're going to have overlap between subproblems. Just like we did in our Fibonacci case, right? We ran into this subproblem of computing Fibonacci of 3, over and over again. Okay, so in dynamic programming, once we compute a result, we just remember the value. And then when we need that result again, we don't have to recompute it. We can just use the value that we've already computed. Okay, so that's kind of the one way to view dynamic programming, is basically recursion, formulating the problem in terms of solving similar subproblems, and memoization, to remember the answer to the subproblems that you've already computed. There's actually another way that you can view dynamic programming, and that is from the bottom up rather than the top down. So we kind of have this recursive top down approach, or we can have an iterative bottom up approach. And the way that you can view dynamic programming in this way is you basically look at your subproblems and you can kind of write them out and look at the dependency graph between these subproblems. So you look at, okay, what subproblems do I need to solve first so that I can then use the answers to those subproblems to solve my other subproblems, right? So for example, in the case of the Fibonacci numbers, the dependency graph of the subproblems looks as follows. In order to compute Fibonacci of 3, we already need to have computed Fibonacci of 1 and Fibonacci of 2. In order to compute Fibonacci of 5, we already need to have computed Fibonacci of 4 and Fibonacci of 3. So we have a directed graph here representing dependency between the problems. And we can just do a topological sort of this graph. Okay, and once we have a topological ordering, then we can just compute the subproblems according to this ordering. And then whenever we get to a new subproblem, we already have the information that we need in order to find the answer to that subproblem. Okay, so this is the alternative view to dynamic programming. You can kind of view it from the bottom up. You look at the dependency graph of your subproblems. You can do a topological sort of that graph, and then compute the subproblems in the order of the topological ordering. Okay, so that's a brief introduction to dynamic programming, and now let's look at some more examples.